video was go over this last section involving the different object locations and finding the image distance and the object distance and the magnification. So in order to do that, let's review where we left off last time. The last thing we talked about was the different rays and the definition of them. Remember that concave and convex mirrors reflect these rays a little differently, but the definition of the rays stays the same. So the first ray, which is the P ray, P as in parallel, is an incident ray that is parallel to the principal axis and is reflected through the focal point. The second one is the F ray, which is an incident ray that passes through the focal point and is reflected parallel to the principal axis. And lastly, we have the C ray, which is an incident ray that passes through the center of curvature and is reflected back along itself. Now we're actually going to start to use these along with the object locations to find the location of the image. What I mean specifically by the object and the image is, for example, if I were looking at myself in a mirror, I would be the object and I would see a reflection of my image. So the object is the thing whose image is being reflected on the mirror. So in this case, we're specifically talking about concave and convex mirrors. Here we have a concave mirror, but generally anything that's in front of the mirror or towards the side, we say is positive, and behind the mirror, we'd say is negative. Okay, so we're going to use the mirror equation later on to find the specific distance of the object. But in general, there are 6 different locations where that object could be. So we're going to go through that first and then later on use the equation to find the exact distance. So the first possible location for the object would be at infinity. We're not going to talk much about this one except at the very end. When an object is this far away from the mirror, its reflective rays are basically all parallel, so you end up not even being able to see the image. So this first case isn't as important. What you do need to know or remember is that C, the center of curvature, is the center of the sphere that the mirror is a part of. So that distance from the mirror to C is the radius, and then the distance from the mirror to F is the focal point. So again, this one is far enough that it's past the radius. It's just very far that you don't even get an image at all, and we'll talk about how that works later on. The second case, which is right here, is a location that is beyond C, meaning that the object distance is going to be greater than the radius of that circle. The third case or third location would be at C, which is the center of curvature. So in that case, the object distance would be equal to the radius of the circle. And fourth, we have the location be somewhere between C and F, in which the object distance would be between the focal length, which is that distance there, and the radius. And then the fifth location would be at the focal point, in which case the object distance would be the same as the focal length. And lastly, we have between the focal point and the mirror, in which case the object distance would be somewhere between 0 and the focal length. Okay, so now we're going to use these possible object locations and our rays to figure out how and where the image would be reflected. So let's start with case number 2, where we have an object that's located somewhere beyond the center of curvature. And I have my mirror, the principal axis, and I'm going to say this is my center of curvature and my focal point. And I want to say that my object is beyond C. So how do I know how this object is going to be reflected? That's where I'm going to use my rays. So I'm only going to use the F ray and the P ray, and you'll see why in a second. So our P ray is the incident parallel ray that is reflected through the focal point, and my F ray is an incident ray that passes through the focal point and is reflected parallel to the principal axis. So what you need to know is that where these rays intersect is where the image is going to appear. So notice here they intersect in a place that is in front of the actual object, so it's closer to the mirror than this one is, and it's also underneath this line. So what does that mean? It means the image, here I'll actually trace the F ray in a different color so you can see. It means this image is actually going to be upside down. So in the case of 2, or when an object is located beyond C, meaning its distance is greater than the radius, you have an image that is going to be smaller, because although you can't really tell here, you can see it better in your book. Just wanted to draw it out for you so that you could see how it looks. You have an image that's going to be smaller than the actual object. It's going to be closer to the mirror, and actually you can see it's between C and F, and it's also going to be upside down or inverted. Okay, so in the third case, where we have the object located at C, meaning the object distance would be equal to the radius, we have an object located at C. Take the parallel ray that goes through the focal point, and then the F ray that goes through the focal point and then parallel. We'll see that our image ends up in the same location as the object, so same location, but the image is inverted. And it's also the same size. Now, just a quick note, I would recommend not relying on your drawing skills to remember what happens in each of these cases, because if you don't draw all the lines the exact same length or the objects the exact same size, you're not going to get the correct location. For example, I tried it a bunch of different times until I actually got it to line up to what it was supposed to. So I would just go off of your book here. I just wanted to draw it bigger so you'd see, since you'd also see how drawing the rays works. Okay, so in the fourth case, where you have the object located somewhere between C and F, meaning the distance is between the focal point and the radius. So our object is located somewhere between the center of curvature and the focal point. So that distance, we say, would be between the radius and the focal length. Our image is going to be reflected if we follow the P ray and the F ray to where they intersect. We see they intersect at a location that is farther than C. So you could say the image distance is greater than the radius. It's inverted, and it's also bigger than the object. Now, something important to know from these three cases is that the image that is formed is known as a real image. That's because it's on this side of the mirror. And these are the only three cases where a real image is formed. In the first case, the fifth and sixth, you do not get a real image. We're going to talk about what those are now. So in the first case, where the object is at infinity, The object is basically so far away that all of its rays are parallel when they meet the mirror. So they're all reflected through the focus, and the image is basically just so small at that point where all the rays meet at the focus that you can't see the image. And so it's not a real image, even though it's technically on the side of the mirror. In the fifth case, we have the object that's located at the focus, and here the rays are reflected so that they actually never intersect. So the image formed by this object is said to be at infinity and infinitely large, so because it cannot be seen, it does not exist. So in the last case, where the object is located between the focal point and the mirror, the rays do not converge or intersect out here on this side of the mirror. Instead, what happens is similar to what happens in a plane mirror, where it appears like the rays are coming from a point behind the mirror. So in this case, you have what we call a virtual image, because it's on this side of the mirror, and this virtual image is erect, meaning it's upright, like the object, and you can see it's also bigger than the object.